Hello all, welcome to the video lecture of Advanced Artificial Intelligence. This is Ramesh Lama, and in this video lecture we will be discussing about the image processing in computer vision. As we discussed in our previous class, the fundamental object of computer vision is the digital image. We discussed about the basics of image formation and representation of image. Before we go further, first of all, let us see why do we need to process the image, or why do we perform certain operations on image, or what are the goals of image processing. Well, the main goal of the image processing is to enhance the visual quality of images for human perceptions, where we do denoising and smoothing operations. We also increase the contrast of the image. Another goal is to extract the information or feature from the image, where we extract texture, edges, distinctive points, and so on. These features can also be used for the object recognition and classification. And there are other purposes of the image transformation or image processing. For example, change in the image resolution and the aspect ratio, and which we can use for the display on the mobile device and other display devices. Now let us see the different image processing techniques in spatial domain or spatial domain methods. The spatial domain refers to the image plane itself, that is a collection of the pixels constituting an image, and the spatial domain process can be represented by the expression which is given by gxy is equal to tfxy. As we discussed in our previous lecture, an image pixels can be represented as a two-dimensional function fxy, where xy represents the pixel location or the pixel coordinate, and f represents the pixel intensity. And as I said before, the processing or transformation of image can be expressed as gxy is equal to t of fxy, where fxy is the original image or the input image, and gxy is the processed image or transformed image, or we can say it as output image, and t is the operator on f, which is defined over the neighborhood of a point xy, and this operator is defined over neighborhood of the point xy in the original image xy. And there are two principal categories of spatial processing, and which are intensity transformation and the spatial filtering. The intensity transformation operate on the single pixel of an image for tasks such as contrast stretching and image thresholding, whereas the spatial filters perform it operates on neighborhood of every pixel in an image. And the neighborhood of a point xy, here we can see the neighborhood of the point xy is usually a square sub-image which is centered at the point xy. You can see here in the figure. And let us look at this figure. Here we have an image f, and which can be seen as an outer rectangle, and within this image we take a point xy, and the neighborhood of this point xy is a square sub-image around this point xy, and this particular has 3 by 3 neighborhood, which is centered around the pixel at location xy in the image f. However, the size of the neighborhood may vary depending on the application. It may be a 5 by 5, 7 by 7, or 9 by 9, and so on. But for now, we will just see we'll look only the point processing or the intensity transformation. So let us see the intensity transformation. While talking about intensity transformations, the simplest form of T or the function is when the neighborhood is of size 1 by 1, that is a single pixels, and when we have a single pixel, then the output or G, the output image or the transformed image, it depends only on the pixel, only on the value of f at xy, and T becomes a gray level transformation function of the form here S is equal to T of R. We can say that R is the gray level of fxy, or the R is the gray level value of the input image or the original image fxy, and S is the gray level of gxy, which is the transformed or output at the point xy. And this type of processing is known as a point processing, because the processing depends only on the gray level at that point. And there are three basic types of functions used for the gray level transformation in image enhancement, which are linear, logarithmic, and power law. We can see this graph shows the different gray level transformations. We can see here linear, that is the identity function here, which is the that is the identity function, which is the straight line, and we can see the log on the upper side of the straight line or the linear function, and the inverse log or the nth power or nth power of which is given by the power function, and this nth root also gives us the power function, and log is represented here. So this block represents the different operations that we performed on the gray level transformations. Let's see the identity transformation. In case of identity transformation, we can see here whatever the input fxy, we get the output gxy. So if it makes no changes on the input image, so the transformation function simply it doesn't perform any operations. Whatever the input is given, whatever the original image, the transformed image will be the same as the input or original image. Now another transformation is the negative transformation. This negative transformation of image with intensity levels in the range of 0 to L-1 is obtained by using the negative transformation function as shown in figure. Here we can see the negative transformation with the function. Here what we can see is in the horizontal axis we see the intensity of the input image R or the original image, and in the vertical axis we see the intensity of the output image, which is S, as we just discussed before. And we can see from the figure that the negative functions reverses the intensity level of the original image. Here we can see it just reverses the output, it just reverses the intensity level of the input, and that means the minimum intensity level or the low intensity values, which is visible as dark in the dark pixels in the image, is transformed to the bright pixels. Like we can see here, the zero intensity level, zero is converted to L-1, and L-1 in the input R is transformed to the the L-1 is transformed to the 0, and 0 is transformed to L-1, and as a result we obtain the negative plot graph. We can see here, this is the negative. Here we have got the input image and we get the negative of this image. We can see this is the original image, which is the digital mammogram, and negative image, which is obtained by using the negative transformation. And we take this image, I took this image from the digital image processing book of Gonzalez, which is a very popular book, and This process is useful in case when the images that we get contain a white or gray label in the gray label information we have got here. Suppose we have got the gray label information here, and it is embedded in the black pixels or very dark pixels, and the nature of information is such that we have a very few white or gray label information present in the black background. We have got this image and this information which is very much dark, like the background is dark, and we have very few gray label images. And now if we find the negative of this image, and we can see in the negative image, like we can see more informations, the gray images, the gray part or the gray pixels are converted to black in the white background, and here these intensities or this information is more visible. So instead of considering the original image, if we take the negative, we can get the required image or the required image content more clear than the original image. So in this kind of scenario, we can use the negative transformation. And another one is the log transformation, and the general form of log transformation is given by this expression here: S is equal to C log 1 plus R. This transformation maps a narrow range of gray label values in input image to the wider range of the output label. You can see here, like this narrow label here, we can see like this lower label intensity level is transformed to the wider range in the output. And we can see here that the higher gray label values are compressed to the narrow. Similarly, we can see here in the higher intensity level, we see it is narrowed. It is narrowed in the output, and this transformation is useful for enhancing the details in the darker region of the image and at the expense of the detail in the brighter regions. We can see here in this image, this is the Fourier spectrum, and we can see the input image. It consists of lots of dark, and this dark part is not that much visible in the input image. But when we perform the log transformation, and in log transformation we can see that the lower range and the lower pixel intensity, lower range information is more visible in this output image. So this transformation is useful for enhancing the details in the darker regions of the image at the expense of the detail in the brighter regions. And if the dynamic range of image is very large, then only few pixels will be visible, and this transformation compresses the dynamic range of the image. And another transformation is the power transformation, and the power transformation, it can be expressed in terms of this expression we can see here, as the output pixel is given by C, the multiplied C multiplied by R, which is the input pixels with the power of gamma. And here C and gamma are the positive constants. We can see here we use gamma as a positive constant and C also as a positive constant, and it can be written also as a S is equal to C R plus this epsilon power of gamma to account for the offsets. And we can see from the expression that S is a function of gamma and R, and let us see the plot of this function with the constant R. We keep the R constant and we vary the if we keep the let's see the, we can see here, we can plot the we can see here the plot with the different values of gamma and input gray level R. Here we can see that as in the log transformation, the fundamental value of gamma map a narrow range of dark input values into a wider range of output, and opposite is true for the higher values of the input levels. We can see here when we have the fractional value of gamma here, when we put the when we set this gamma value to be fractional, and and we perform this operation, we get this as same as log transform, that does the what we like it does that the narrow range of dark input values are converted into the wider range of the output values. We can see it's same as a log transformation, and with the gamma value greater than 1, it is just the reverse of this. It is just the reverse of this function, like it is just the reverse of log function. And this kind of function is useful for the variety of devices that is used for image capture, printing, and display. And in this kind of devices, the display those display respond according to the power law. And here we can see that if we display the original image without any power law transformation, and here we can see that the original image is viewed in the monitor without any transformation, and that like the intensity level is can be seen differently than in the original image. However, if we correct the gamma, or we perform the gamma correction, or we perform the gamma transformation or power law transformation, and then display it on the same monitor, then we will get we can see same as the original image. So this kind of operations, this power law transformation, is used for in most of the case for the display. And in case of monitor, we set gamma value to be 2.5, and this is used for the gamma correction. This is this term we call the gamma correction. So with gamma correction, what we see here is that the original the displayed image and the original image look similar, but if we don't perform any gamma correction, then the original image can be seen different. The displayed image can be seen different to the original image. And the power law transformation can also be used for the contrast enhancement. We can see here with different values of gamma, with C set to 1, and with different values of the gamma. We can see here, like with the gamma value set to 0.6, 0.4, and 0.3, we can see here the original image and the transformed image with different gamma value. Here what we can see is we can see more details, or the contrast of the image, or the more details of the image can be shown in the gamma corrected image. We can see here we can easily find the difference between the image at figure A and figure D. Like here, some of the unseen content of this image can be seen in this gamma corrected image or the transformed image. Similarly, we can see this as well with the different values of gamma and the original image. It looks like a blur, or it is not, some of the content of this image cannot be seen clearly, but in case of gamma corrected image or transformed image, power law transformed image, we can see here the gamma value is set to 3, 4 and 5, and the constant values and C is set to 1. And this is all about the power law transformation. And next is we are going to discuss about the contrast stretching. And first of all, let's see why do we need the contrast stretching. In many cases, due to the poor illumination and the lack of dynamic range in imaging sensor, or even the wrong setting of the lens during the image acquisition, image may have a low contrast, or the pixel value may lie within just the small range of this pixel range. And in such case, the contrast stretching expands the range of the intensity levels in the image, so that it spans over the ideal range of the intensity level. We can see here that the pixel intensity will be that will range within the value of 0 and 255. And let us see, here we can see an image which is low contrast image, and here we can see that the contrast or the intensity range is very, very poor, and overall appearance of the image is also unclear. We cannot see, the appearance looks unclear. So we perform contrast stretching, and so that the dynamic range of the image is increased, and the different details of the image can be clearly visible. And typical example of contrast stretching can be seen in this figure. We can see here. And here what we do is, here we find in this particular transformation, we have selected 2 points, R1S1 and R2S2. This is the transformation function TR. We have got the input gray level R, output gray level S, and this transformation function TR. And we select 2 points, R1S1 and R2S2. And these 2 points, R1S1 and R2S2, controls the shape of the transformation function TR, and accordingly, and it influences upon that the contrast enhancement, or we can say the level of contrast enhancement may vary. We may vary the level of contrast enhancement according to the value of these 2 points. Now let's see. Let's change the different. Let's change the value of R1S1 and R2S2 and see what's the response, or how this transformation function works. Let's see here. If we set R1 equal to S1 and R2 is equal to S2, here if we set R1 equal to S1 and R2 is equal to S2, and then this transformation function becomes a straight line here. This is this straight function, or we can say this as the identity transform, as we have discussed before, and with the slope of 45 degree. And this means that whatever the intensity of the input image, the processed image will be the same intensity. There is no change in the intensity of the transformed image. Next, now if we make here another, R1 is equal to R2, here R1 is equal to R2, here R1 and R2 is same, and S1 is set to 0 and S2 is L minus 1, then this is called the thresholding function, or it creates a binary image. Like here the output image will be either dark or light, and so the transformation generates the binary image. And we can see here, we can call this the thresholding function here, and this is our input, and output image will contain either 0 or 1, or at the maximum value or the lowest value. So this enhanced image is this we call the thresholding, and we get binary image with this setting of R1, R2 and S1, S2. And another way is, now for enhanced image, usually we set R1 is less than R2 and S1 is less than S2. which gives us the transformed image as shown in the figure. This one, this is our original image with the low contrast, and here is the, when we set R1 to be less than R2 and S1 to be less than S2, what we get is we get some kind of this transformed image. Here this is the contrast stretched image, and here this is the binary image that we have just discussed before, and in this way we can get the contrast stretched image. And another technique is the gray level slicing. Here what we do is we perform some specific range of intensity, like we highlight some specific range of intensity. Here we can highlight it in two ways. Like in one case, what we do is we set we just highlight the certain pixel value and rest of the pixel are set to 0. This can be visible here. And another one is we set we let other pixels to remain same, and just we highlight the some pixel values, and we can see here this is the transformation of A and B. Transformation highlights range A, B of the gray levels and reduces all other level to 0. And the another figure shows that the transformation highlights the range but preserves the all other level, all other images. Here also is the same, like we have the aortic. This also performs the same as in the previous one. And this all for the intensity transformation.